childlike understanding of space and time. First Einstein's special theory of relativity, and then Einstein's general theory of relativity, where space and time became dynamical entities. And I believe that we're going to see more. For example, one question that is now asked quite seriously, experiments are being performed to probe this question, is are there more than 3 dimensions of space? Some of our theories require more than 3 dimensions. Why not? In string theory, for example, there are at least 6 more dimensions curled up into a marvelous little curled up manifold. This is a 6-dimensional, beautiful manifold that describes some of the solutions to string theory. And remarkably, when you take string theory, which one way of looking at describes little closed loops of energy strings moving in 9 spatial dimensions, and you curl up 6 of them into a manifold that is described, that you find, you construct the manifold by solving the analog of Einstein's equation, the nature of the forces that you observe at large distances, the form of matter, the values of their masses, and all the things we can't yet calculate are determined by the shape of the hidden dimensions. Anyone read this? No. Can you make it lighter? Good. That's proof that somebody can read it. In our current speculations about quantum gravity, especially in string theory, we are beginning to suspect that our notions of space-time, which have been revolutionized so much from the way Newton or Galileo thought about space and time, will still require radical revision. This is the quote of 2 famous string theorists at Witten, who was my student. Space and time may be doomed. Nadi Steinberger, another graduate of the Weizmann. I'm almost certain that space and time are illusions. So what does it mean? So physicists are beginning to believe that somehow space and time are illusions. In fact, we believe more and more that space and time are emergent concepts. We actually have a lot of evidence within string theory that space is an emergent concept. We have basic formulations, which are the most powerful formulations we have of the theory, where space is an emergent concept. That means that you start with a theoretical framework in which you never mention space. You just derive it as a way of describing large objects in the classical approximation. What we don't yet have is any example or understanding of how we can do that with time. How time, which is a little different in space, can be emergent in the same way. But this is a question that is at the forefront of modern physics, and I hope again will be answered in my lifetime. What is space-time made of? And now, finally, I'm going to end with a few remarks about biology, more specifically the kind of biology that theoretical physicists are interested in, which might be called theoretical biology, except that biologists tend to give me trouble, or if we talk about theoretical biology, they talk about system biology and things like that. They don't like the word theory, but physicists do. And they have, over the last few years, decade or more, been more and more turning to studying living matter. The distinction, of course, between biology and physics is absurd. Helmholtz, in the last sentence, physicist, biologist, both. But these distinctions get created by university departments. Living matter, as we just heard in the last lecture, is incredibly complex and exhibits the marvelous property of self-organization and creation of matter. And this is something that physicists have been interested in and studied in inorganic or non-living matter for many years. They think they might have something to contribute. And in fact, in my Institute of Theoretical Physics, now about 20% of our activities are in what might be called theoretical biology, not biophysics, where you have physicists having some instrument or tool trying to apply it to a biological system, but rather theorists or physicists who become interested in biology and the questions posed by nature and come simply with their arsenal of way of thinking that characterizes physics. But it's not clear that there is a theory of biology, that there are universal phenomena, that there are explanations of the type that physicists are accustomed to. And many biologists will argue that biology, or what we observe in living matter on our planet, is a product of, it's of course a product of natural selection, but it is a historical accident that you have no chance of constructing a theory of. Others would argue that they're bound to be universal features. Who knows? Can theoretical physicists help? Well, they certainly would be more likely to help if there is a theory, universal features and laws. Is new mathematics required? This is an interesting question. Some of my physicist friends who moved into biology believe that new mathematics will be needed. In fact, old mathematics, or mathematics, developed over the centuries together with physics. Calculus was invented by Newton to solve, to understand, calculate the orbits of planets. Partial differential equations were evolved in the 19th century with field theory and heat conduction and so on. Mathematics developed together with physics and in response to the natural world, but mostly the non-living matter natural world. Perhaps to describe living organisms, new mathematics will be required. There's one reason that might be so, and why living systems are so different than the systems that physicists have tended to study and understand. And that is that biological systems have dynamics over many, many wide-ranging timescales. In physics, we're used to, we've made progress by being able to make a separation of scale. So as previous lectures didn't have to worry about what went on inside the nucleus. It was irrelevant, and in fact, the chemist barely has to worry about what goes on inside atoms. And so there's a clear separation in studying physical systems. We're able to separate the scales and make progress. If in order to understand chemistry, one had to understand nuclear physics, it would have taken a lot longer, believe me. But in biology, there's dynamics over many different scales, especially in the time domain. For example, I am talking to you now, and there are chemical reactions going on in the synapses of your neurons, if you're not sleeping, that act on a very short, microsecond less time scale. And they might very well, I hope, imprint themselves on that cell. Possibly will take sometimes days to finalize the creation of a memory. And you might remember 10 years from now this lecture and say, oh, I remember Gross said that and that. He was totally wrong. So what I say now and